Okay, number 15, the third question in Unit 5 progress check. This is the number of mosquitoes in a field is modeled by the function defined as m of t such and such from 0 to 18. I'll let you read this and understand this, but I want you to, when you're looking at these types of problems, or really any type of problem, it's not a bad idea to look at all sections just really quickly. All right, so we're looking for what does this mean? I think we can understand what that means in a second. Based on the model, the absolute maximum. So when we look at this, we're looking at two things. We're looking at our end values, 0 and 18, and any value in between where the derivative equals 0. So we're feeling okay about that. Is the rate of change of the number of the mosquitoes increasing? So we're talking about derivatives here and setting it equal to 0 and determining what intervals it's positive or negative. Specifically in this case, positive for increasing. And then lastly, the number of bats in the field is modeled by the differentiable function b, where b is a function of the number of mosquitoes. Normally, we're talking about function of x or function of time, so f of x or f of t. In this case, function of the number of mosquitoes. So this is b of n. So this is the number of bats is connected to the number of mosquitoes. Therefore, we're doing b of n, and we'll talk about that in a little bit. Okay. So part A, it says very straightforwardly, at time t equals 15 days, the number of mosquitoes in the field is decreasing at a rate of 171 mosquitoes per day. So using the right units, so we're talking about number of days, we're talking about decreasing because it's negative. All right, so just understand what this means and be able to put that into words. Part B, based on the model, what is the absolute maximum number of mosquitoes in the field over the interval? So we have to take the derivative. This is because it's a non-calculator problem. This is going to be a easily factorable problem, or relatively easily factorable problem. We take out our GCF. This factors down to t minus 12 and t plus 4. And we know that m prime of t is equal to 0 at t equals 12. We also know that it's equal to 0 at negative 4, right? So, but this is not in the domain. Negative time, negative number of days doesn't exist. So our three critical or test values are 0, 12, and 18. And when we calculate, this is increasing from 0 to 12 because we tested the 10 value in this function. And remember, this is negative, so we have to count this in our calculation. Negative, negative, positive, therefore positive. We plug in 14, we have negative, positive, positive, therefore that's negative. So we need to pay attention to the negative 3 here. Oftentimes, we discount this factored out term, but it's only because it's either squared or e or something where it's always positive. So we don't concern ourselves with it. Because it's negative, we have to concern ourselves with it. This is our absolute maximum because 0 gives us 0. It increases over this entire interval, 12, and then it decreases again. It never changes direction again. So there's no concern that at 18 days, we're going to have more mosquitoes. So we can look at this as our absolute maximum value. And they don't ask us for the value. They just say when. Okay. I take it back. They do say what is. So at this point, we take 12 and we plug it into our original function. Okay, so I stand corrected. They do want us to give us the actual number. So we determine that it's 12, and then we plug that into the actual function. A little bit of math here. I'm a little surprised they gave us this math without the calculator. But again, we will always have a calculator available to us. Okay, so in this case, for what values of t is the rate of change of the number of mosquitoes in the field increasing? So we're not looking for when is the number of mosquitoes in the field increasing. We're looking for the rate of change. When is the rate of change increasing? So that's the second derivative. Again, if this said for what values of t are the number of mosquitoes increasing, then it would be the first derivative. But what this is saying is for what values is the rate of change of the mosquitoes in the field increasing. Therefore, we're looking at the second derivative. So the second derivative is negative 6t plus 24. We set that equal to 0. We take out our GCF and we find out t equals 4 is our critical value. And this right here, they know that when t is less than 4, it's positive. But what we want to do maybe real quickly is do a quick plus minus chart for us. And notice that when I plug in 3 here, this becomes a negative times a negative or positive. When I plug in 5, it becomes negative. So it's increasing from 0 to 4. So the rate of change of the number of mosquitoes in the field is increasing from 0 to 4. Okay. And last problem, for T between 0 and 18, the number of bats, we already talked about this part. But what this means is this right here, B of M of A. And what this means is, if we're looking for the rate of change, we need to use the chain rule. So when we take the derivative of this function right here, it becomes the derivative of the outside, B prime, normal inside, that's my M, okay, or M of A, times the derivative of the inside. And we just write this out just like this. B prime, we know, we have no idea what B is, so then we just leave this as B prime. This is our original mosquito number function times, this is our derivative of our mosquito function. This is M prime of A. And that's it. So the question is, write an expression for the rate of change of the number of bats. Well, the rate of change of the number of bats would be the derivative of this, and this is our solution. Do not go through this and multiply this through. There's nothing to be gained. That is your answer.